Improper integral. If f of x is non-negative, then the definite integral from x equal a to x equal b of f of x dx represents the area under the curve f above the x-axis from x equal a to x equal b. If we take b to infinity, then the enclosed region is now unbounded. We might think, therefore, the definite integral is not bounded or infinity, but this is not always true. For example, the integral from 1 to b of 1 over x to the fourth dx, what happened to this integral as b goes to infinity? We attempt to evaluate this integral by first finding the antiderivative of x to the negative fourth. We then use the fundamental theorem of calculus to evaluate this expression at b and 1. The result is 1 minus 1 over b cubed over 3. As b gets larger and larger, b cubed gets even larger, and 1 over b cubed gets smaller. Thus, at b go to infinity, 1 over b cubed approaches 0. Thus, 1 minus 1 over b cubed over 3 remains less than 1/3. That means this integral will remain less than 1/3. Properly, we essentially take the limits at b go to infinity of the integral 1 to b 1 over x to the fourth dx. If we take the limit of this integral, then we take the limit of the result. This limit is 1/3. This example shows that even though b, the upper limit of integration, is approaching infinity, the region is unbounded, thus the area under the curve is finite. Integrals over unbounded intervals. Suppose that for a fixed a, f is integrable on the interval a, b for all b greater than a. If the limits at b go to infinity of the integral a to b f of x dx exists, we say that the improper integral a to infinity f of x dx is convergent, and we define its value by the integral from a to infinity of f of x dx equals the limits at b go to infinity of the integral a to b f of x dx. Similarly, if for a fixed b, f is integrable on the interval a, b for all a less than b, we define the integral from negative infinity to b f of x dx as the limits at a go to negative infinity, the integral from a to b f of x dx if the limit exists. And finally, if f is integrable on the interval a, b for all a less than b, we define the improper integral negative infinity to infinity of f of x dx as the integral from negative infinity to 0 f of x dx plus the integral from 0 to infinity f of x dx if the improper integrals on the right-hand side are both convergent. If an improper integral is not convergent, it is called divergent. Note that the reason why we call these integrals impropers because the upper or the lower limits of integration is not a finite number, but rather infinity or negative infinity. Integrals with unbounded intervals is called type 1 improper integrals. For example, for which values of the exponent r is the integral from 1 to infinity x to the r dx convergent? We first set up the improper integral properly by taking the limits at b go to infinity of the integral from 1 to b x to the r dx. This is equal to the limits at b go to infinity of x to the r plus 1 over r plus 1 by using the antiderivative of x to the r. We then evaluate it from x equals 1 to x equals b. This simplifies to the limits at b go to infinity of b to the r plus 1 in the exponent minus 1 over r plus 1, where r needs to be not negative 1. If the exponent r plus 1 is positive, that is, r is greater than negative 1, then the term b to the r plus 1 approaches infinity, or that limit doesn't exist, so the entire integral is divergent. If the exponent r plus 1 is negative, or r is less than negative 1, then the limit of the term b to the r plus 1 go to 0 as b go to infinity. It is because the exponent of this positive number b is negative. But if the term go to 0, then the limits of the integral is negative 1 over r plus 1, where r is less than negative 1. This number is a finite number, so the integral is convergent. If r plus 1 equals 0 or r equals negative 1, then the integral is ln of b, but as b go to infinity, ln of b go to infinity, so the integral is divergent. Thus, the values of the exponent are such that the integral from 1 to infinity x to the r dx is convergent is when r is strictly less than negative 1. This result is known as the p-integral, the integral from 1 to infinity of 1 over x to the p dx. So in this case, p is negative r. Replacing r with negative p, we see that the integral from 1 to infinity of 1 over x to the p dx is convergent if p is strictly greater than 1. This result is used quite often, so we will summarize this here. The improper p-integrals, the integral from 1 to infinity of 1 over x to the p dx, is convergent if p is strictly greater than 1 and divergent if p is less than or equals to 1. The result is also true if the lower limit of integration is a number that is more than 1. For example, the integral from 2 to infinity of 1 over x squared dx, since p equal 2 is greater than 1, we know that this integral is convergent. Or the integral from 10 to infinity of 1 over the square root of x dx, in this case p equals 1/2, which is less than or equal to 1. Thus we know that this integral is divergent.